Good morning, everyone. So, we are on the way of looking into various models of membrane-based separation processes under various domains, whether it is osmotic pressure control or it is a gel layer control and things like that. And in the last class, what we did, we just looked into the the modeling part of gel layer control filtration. So, we divided the whole exercise into two parts. One is the steady state part, another is the transient part, then hooked it up with the steady state, and finally we looked into various parameters of the gel layer control filtration model, which is basically mimicking the cake filtration model, and how to evaluate these various parameters almost independently compared to an actual experiment. Okay. Now, in today's class, we will be first, there are two parts. We will be looking into we just look into other models which will be basically used to overcome the shortcoming of the film theory, and then we will be going to the design of the modules, and I will let you know that means what is so important about the design of the module and why we are going to do once again for this part. Now, let us look into the just have a brush up of shortcomings of film theory. Number one was the mass transfer boundary layer is assumed to be of constant thickness, and in an actual process it is really developing over the channel length or period of time. Second one was that mass transfer coefficient that we are going to use, it is used for non conduit. Thirdly, the physical properties are assumed to be constant, On the other hand, the physical properties like the chemico-physical properties like diffusivity, viscosity and density, they are functions of concentrations, and among these three the viscosity is the strongest function of concentration. Now, we have seen how this mass transfer boundary layer, the developing mass transfer boundary layer will be taken care of in a two-dimensional model. So, we have already done that. Secondly, the mass transfer coefficient that is used for the non-porous conduit, that is obtained from heat and mass transfer analogy, how it will be corrected for for a porous membrane surface, that we have already seen, and we have utilized some of these derived some of these mass transfer coefficient equations. Then third one, the physical properties are assumed to be constant. This limitation we have not seen till now, and it will be really interesting how to incorporate the variation of physical properties as a function of concentration. Now, let us list once again what are the physical properties we are trying to talk about: diffusivity, viscosity of the solution, and density of the solution, thermophysical, chemical-physical properties. Now, out of these three, viscosity is the strongest function of concentration, and diffusivity follows, and density becomes a weaker function of concentration. This is stronger, this is strong. In fact, this is not enough. In fact, the density as a function of concentration is the weakest one. Now, if we look into the we have already talked about the osmotic pressure control model, we have already talked about the gel layer control model. In osmotic pressure control model, the membrane surface concentration will be around 10 times, maximum it will be around 10 times of feed concentration. On the other hand, in most of the cases it will be 3 to 4 times of feed concentration. And on the other hand, in the case of gel layer control filtration, the gel concentration, that is the wall concentration on the membrane surface, it becomes sometimes very, very high. It becomes 40 times of feed concentration, sometimes it becomes 50 times of feed concentration, so on and so forth. So, in case of gel layer control filtration, and the variation of concentration in the concentration boundary layer from C0 to Cg is maximum. and in osmotic pressure controlled filtration also within the mass transfer boundary layer, it gives a significant variation of concentration. So, therefore, the variation of concentration in terms of the property variation has to be taken care of in the model. So, how to do that? The first approach that generally is taken is the mass transfer coefficient is modified. Coefficient is modified, and what is the modification? The modification is an empirical factor is generally incorporated like Sider-Tate factor, in heat transfer. So, what is the variation? The variation is the Sherwood number, this becomes 1.85 Reynolds Smith d by L raised to the power 1 upon 3. There we incorporate a factor mu bulk by mu at the membrane surface raised to the power 0.14. Okay. Now, it may, in fact, this is an adjustable parameter. So, what is this? This is the Sherwood number without taking the property variation, and this is the correction factor because of the variation of mass viscosity between the bulk and the membrane surface. Similarly, if it is a gel layer control filtration, it will be this mu m will be replaced by mu at Cg. Okay. Mu b is nothing but viscosity at bulk concentration, and mu m is nothing but mu viscosity at the wall concentration, or Cm or Cg, depending on the controlling regime you are talking about. Now, in order to, there is another modification of this equation. If you would like to, so what this equation tells, it gives only the variation of viscosity within the concentration boundary layer, because it is the strongest. Now, if we would like to incorporate the variation of diffusivity and density as well as a function of concentration, this will be slightly modified, and this becomes SH under subscript m, means it is a modified version 1.85 Reynolds Smith d by L raised to the power 1 by 3. This will be Smith number at bulk divided by Smith number at membrane surface raised to the power 0.14. Now, so it is basically mu by rho d at bulk concentration divided by mu by rho d at membrane surface concentration or gel layer concentration. Now, there is debate on this coefficient 0.14. Now, it has been generally found out this coefficient varies between 0.11, let us say if this is n, this n varies between 0.11 to 0.27 depending upon the situation or the system that you are going to have. That means, you measure the viscosity as a function of concentration. Okay. So, you will be getting some, that will be easy to measure. So, then you fit a curve. Okay. Similarly, the variation of diffusivity as a function of concentration will be also available from the literature. Okay. And density, you can measure different concentration, you can prepare different concentration of solution and measure its density. So, that can be again expressed as a function of concentration, and this whole Smith number can be expressed as a function of concentration appropriately, right. Then the whole thing will be, it can be utilized in order to calculate the permeate flux or permeate concentration. Now, if you would like to incorporate the effect of suction, now this will be modified by the Sherwood number expression that we have already obtained in our earlier in terms of Pw and Pw square, lambda square, lambda cube, something like that. So, that will be inserted here, on addition the viscosity variation factor or the property variation factor. Okay. Now, this is valid for I have written the Sherwood number expression for a laminar flow. This is valid for turbulent flow as well. So, if the flow regime is turbulent, the Sherwood modified becomes 0.023 Reynolds Smith d by L raised to the power 1 upon 3 divided by Schmidt of bulk Schmidt at membrane surface raised to the power n. Okay. So, this is an empirical approach. To take care of property variation because of the concentration variation within the mass transfer boundary layer. Now, there are fundamental approaches is also there, but this becomes very complicated. Okay. In fact, one of my students, he really attempted this type of problem, and this problem area he solved it. So, you can look into separation and purification technology. Bhattacharya et al. And just give this search, it will the article will come, and you can just read the article, download the PDF and go through the article, then you will understand what it can be done if you incorporate, if you would like to try to incorporate the variation of property from the very fundamental, from the first principles. Okay. Otherwise, this correction factor, sedated correction factor, is good enough for a preliminary starting of solving this problem. Okay. Now, we have almost completed all the fundamental models. Those will be applicable in case of membrane based separation processes. And now, one more model is still there, and that is called resistance in series model. Okay. So, in this case, it is assumed that all the resistances are in series. For example, if you have a membrane there, so the whole thing is looked as if there are all the resistances are put in series, and it is a series circuit. It is a membrane surface membrane hydraulic resistance, then you will be having a gel layer type resistance. Okay, a gel layer is formed, so it is Rg, and over and above you will be having a boundary layer, concentration boundary layer formation, and that resistance we assume as RBL. Then the pores may be blocked, and you will be having an irreversible fouling. That irreversible fouling resistance is known as R irreversible. Okay. Then it is assumed that the permeate flux, that is J, we have indicated as J. J is nothing but the driving force divided by all the resistances. But all these resistances are really not known to us. So, it is known as the black box approach. What can be done? We can independently evaluate the value of membrane resistance, we can independently evaluate the irreversible resistance, and we can independently evaluate the gel layer resistance, but we do not know what will be the value of boundary layer resistance under the different operating conditions. So, therefore, what is done, these resistances, knowing these resistances, this boundary layer resistance is evaluated from various operating conditions. Okay. So, this is, and then fit that boundary layer resistance with the operating conditions using a polynomial or some kind of fit. So, this is entirely an empirical approach. Hence, there is lack of fundamental principles involved in this type of modeling, but why we are doing that? These models are sometimes very useful or handy when we are going to test or model a situation when we are using an industrial effluent. An industrial effluent contains lots of components ranging from means it will be, there may be hundreds of components with various values of the thermochemical-physical properties, and it will be very difficult even to analyze those samples, component wise, compound wise, and to get the exact variation of all the property. So therefore, you cannot do anything. You cannot have a value of diffusivity, you cannot have value of viscosity, you cannot estimate the value of density properly. So therefore, in that case, this black box approach becomes very handy, and one can do some small experiments in a laboratory scale, and let us say around 10-15 experiments, and then fit the flux decline data with the operating conditions with the empirically, and then that will be inserted into the model, and that model can be later be used for scaling up under the same range of operating conditions and with the same fluid or effluent. Okay. So, in that case, the resistance in series model becomes quite handy. So, in case of complex effluent, industrial effluent, this becomes handy, and then this may be used in for a prediction of the system performance. Now, next we will go to the modeling of membrane modules. Now, let us say what are these modules? Modules are nothing but the housing of the membrane system. Now, when you talk to any industry person or any person, they will always say, okay, you are talking about the membrane separation system, it becomes very costly. The point is, membranes are not very costly. 1 square feet of a good membrane is only about 70 rupees or 80 rupees, or let us say around 100 rupees in India. Okay, in fact, that is a very good quality membrane. But the point is, the housing of the membrane it becomes very costly, and that is there comes the modules. So you can have the plate and frame module, different types of modules, plate and frame. You can have spiral wound, you can have hollow fiber, you can have tubular. Now, in case of plate and frame module, it is basically there are 2 plates, okay, 2 parallel plates are there, and these plates are the corrugated plates, and over you place a membrane on the bottom surface, you place a membrane on the top surface, and then the 2 flanges are tightened. Okay. So, you will be getting the 2 surfaces, and when the feed is entering at a high pressure, the permeate will be coming out from both the sides. Now, in one frame, so you can have number of frames, okay, in series. So there can be, you can have in a small volume number of frames, let us say 20 or 25 some such frames, and you will be having double number of membrane areas. Okay, so in a small volume you can have large membrane surface, and this is known as plate and frame surface. Of course, the geometry is rectangular coordinate. On the other hand, in case of plate and frame, if you would like to increase the number of plates, the system becomes voluminous. So what they do, they use a novel design that is called spiral wound module. What is that module? It's basically nothing but the flow through rectangular channels, and you can put lots of such channels over one above the other, separated by the separator of the spacers, and then this whole sandwich, suppose there are 8 number of such channels, okay, this is called a sandwich. This whole sandwich is spirally wound around a central axis. Then your space requirement becomes less. But if you open up a spiral wound module, it becomes nothing but a flow through a flat plate, flow through a rectangular geometry. That is one. Third one is the tubular membrane. In tubular membrane, it's basically a tube, and the inner surface of the tube is made of the membrane. So it's basically you will be having, instead of L into W, you will be having pi dl as the surface area. And the last one, that is the hollow fiber one, that is quite used in industry. You can have very small number of fibers. Suppose you will be having porous fibers, which will be having an inner diameter around 0.5 millimeter or so. So you can in a bigger tube, you can pack, let us say, huge number of such fibers, hollow fibers. Okay, in let us say in a 1-inch tube, you can pack around, let's say 1000 or let's say around 10,000 of such fibers. So, you will be having the surface area in this case will be pi dl, that is the surface area for one fiber. This d will be extremely small, length may be let's say 1 meter or so, or even half of a meter, but your n, the number of such fibers will be extremely high. So, therefore, the total surface area becomes very high. So, you can have very high surface area in a small volume, so that you can handle a very large throughput of your system. Okay. So, in fact, in case of hollow fiber also the geometry becomes flow through a tube. So, the geometry for the calculations will be a radial coordinate. In case of hollow fibers as well as the tubular membrane. In case of plate and frame and spiral wound model, it is basically rectangular coordinate. So, you will be having flow through a parallel plates for plate and frame and spiral wound module, and you will be having flow through a tube in case of hollow fibers and the tubular module. Okay. Now, why we have already looked into several models of membrane based processes, why we are doing the modeling of these membrane modules are important. The important simply because there will be in an actual system, we have already seen that in an actual system there will be, what we have done till now, that for the modeling we have assumed that transmembrane pressure drop is constant. Okay, that is valid for a small length of the system, let's say 1 meter or so. But in an actual membrane model, it will be probably several meters of length. In that case, the pressure drop becomes significant. So, whenever there will be a significant pressure drop, you have to ensure that your pump is such a capacity that it can overcome that much pressure and maintain a particular pressure throughout almost the whole module, and then it can deliver the liquid at the end of the module. So, therefore, pressure drop calculation becomes very important when you are talking about the design of the pump that will be driving the fluid into the system. Okay. So, in this case we will be doing the almost same type of modeling, but delta p is a function of x, and how that will be affecting your model calculations, etc., that we will be looking into it, and that is why the modeling of membrane modules becomes very, very important. Okay. And we will be doing now the modeling of the membrane modules becomes very complicated. So, we will be taking some simplified approach. Actual membrane modeling, module modeling should be 2-dimensional or even 3-dimensional in some cases, but that will be entirely out of scope of this course because that requires numerical simulation. What we will be doing? We will be doing simplified versions. We will be using, first we will be using 1-dimensional modeling. Even you cannot have analytical solution if unless and until you do further simplification. Okay. So, even in the simplified version in the 1-dimensional modeling, we will be taking up 3 cases. Case 1, permeate flux is constant. That means at a constant rate you are drawing the permeate out of it, but we have already seen this is not the case. Permeate flux is basically a function of x. Okay. So, in case number 2, permeate flux is constant, and in case number 2, permeate flux is proportional to transmembrane pressure drop. So, J is equal to LP del P. Okay. So, that means we are assuming J is equal to LP del P. That means we are assuming that the effect of osmotic pressure will be much less, negligible compared to the transmembrane pressure drop. That means negligible of osmotic pressure. And case number 3 will be case 2, but osmotic pressure difference is significant. Okay. So, even in this we will be doing a one dimensional modeling, and in case number 1 and case number 2 we will be getting the analytical solution. For case number 3 we will not be getting an analytical solution, you have to go for the numerical simulation for this case. So, basically what we are doing, if you look into the case number 1, 2 and 3, we are basically increasing the complexities of the model and trying to and approaching a more realistic model. So, case number 3 is a more realistic model in under one dimensional, but if you really go the actual modeling, that goes for the two dimensional calculations, and that becomes entirely numerical from the very beginning. Okay. So, what we will be doing case 1, 2 and 3, so that the increasing complexities of the can be incorporated into the modeling, and we will see how that will affect the system performance. Okay. So, case 1, permeate flux is constant. Okay. And we will consider in first case we will consider the flow is through a rectangular conduit. Rectangular channel, and the assumption that this is valid for a plate and frame module or a spiral wound module. Okay. Now, there are several assumptions are involved in this modeling. Let us first list down all the assumptions. Number 1, flow is steady. Okay. Secondly, no concentration build up over the membrane surface. That means there will be no resistance against the solvent flux because of the presence of concentration boundary layer. That will ensure that the permeate flux is almost constant. Okay. Permeation rate is much less than the bulk velocity. That means if your bulk velocity will be around 1 meter per second, the permeate velocity will be in the order of 10 to the minus 6 meter per second. So, it will be that really happens there, and the flow regime is laminar. At the end of this exercise, we will look how the flow regime will change, or the governing equations will be changed once you change the flow regime from laminar to turbulent. Okay. So, with this we will be starting the module design, and let us say we have a geometry something like this. This is a channel height, this is the middle of the channel. The Q in is the flow rate, that is of the feed that is going into the system. Q out is the flow rate that is going out of the system, and H is the half channel height. In and outlet flow rate in meter cube per second, and you will be having a constant suction or constant permeation rate from the walls, that is J from both the walls. Now, for a slit with the impermeable wall, then the using Navier-Stokes equation, you can calculate that q is nothing but 2 h cube by w divided by 3 mu minus dp dx. Okay. So, this comes from the Navier-Stokes equation. If you solve the equation of motion, this is the flow rate, where w is the width of the channel and mu is the viscosity of the fluid, dp dx is pressure gradient. This is the absolute pressure that is present in the channel. Now, this equation, let us look into this equation. There is a limitation of this equation as far as the present case is concerned. The limitation is this equation of motion, this equation that is derived from equation of motion, it is valid for impermeable wall. Okay. But in our case, the wall is permeable. So, but the thing is, the permeation rate is extremely small, probably 3 to 4 order of magnitude less compared to the bulk velocity. So, we can safely use this equation as the for the equation of dp dx, the pressure gradient in the channel. So, this is valid for your membrane system because the permeation rate is much smaller in order of magnitude compared to the bulk velocity. Now, what is P? P is the pressure at any location in the feed site, in the feed channel, right. But what is the transmembrane pressure drop? We require a transmembrane pressure drop to use the Darcy's law. The transmembrane pressure drop delta P as a function of x, that means at any x location is nothing but P at that location minus P atmosphere or the P permeate, right. So, that is the transmembrane pressure drop at any x location, P in the feed side minus P of the permeate. In most of the cases, permeate pressure drop is atmospheric pressure, it is open to atmosphere. So, therefore, dP dx in the Navier-Stokes equation or in the other earlier equation is nothing but d delta P dx. So, the P that is given there is not that indicates the transmembrane pressure drop at any x location. Okay. So, that is identical. Now, we will do an overall material balance. So, we consider a differential element located at x and located at x plus delta x. Okay. So, the total material that is going into the system will be nothing but rho times q, that is at x, okay, and the material that is going out is nothing but rho times q, that is located at x plus delta x, right. And the material that is going out from the wall, that means the permeable wall, will be nothing but rho times rho permeate multiplied by j times, this is dx, right, this length is dx. So, j times 2w dx. Okay. So, this rho p is basically nothing but rho water, it is almost clear water, and j times 2 j is nothing but meter cube per meter square second, and this is the meter square w times dx of this differential element, and there are two surfaces. So, one from the bottom and one from the top. So, therefore, this factor 2 is coming. So, this gives you the total material that is coming out of the wall. Now, if you do a material balance at the steady state, let us see what you get. At the steady state, you will be getting a rate of accumulation is nothing but rate of material in, rate in minus total material, rate of material that is going out plus generation if there are any, minus rate of consumption if there are any. Now, in our case, there is no generation, there is no consumption, there is no accumulation also, because it is a steady state. So, you will be getting rho at q at x minus rho at multiplied by q x plus delta x minus rho p j rho p j 2 w dx, that is the area, should be equal to 0. Now, we assume that as we have already discussed, that density is the weakest function, has the weakest functionality with respect to concentration, and we assume that the density of the fluid as well as the permeate are more or less equal. So, under that case, you can have this equation, you just multiply it this by delta x. So, this becomes q x plus delta x minus q at x divided by dx is nothing but delta x is equal to 2 w j with a negative sign. So, what is this? This is the left hand side is nothing but dq dx, right. So, we get the governing equation of flow rate as a function of x, how it is changing. So, dq dx is nothing but minus 2 w j. So, that is the governing equation of the flow rate as a function of x. So, it is basically the with the negative sign means the flow rate will be decreasing as you go along the x. Why it will be decreasing? Because you are extracting some of the material out of it. Okay. Right. So, then what we will do? You have the governing equation of q earlier, and we insert that. If you look into the governing equation of q in terms of pressure gradient, you had q is nothing but 2 h cube by w by 3 mu minus d, dp dx is nothing but d delta p dx. Okay. So, you can substitute that here and you will get the governing equation d square delta p by dx square is nothing but this minus minus will be cancelled, 3 mu by h cube j. I think this is the governing equation for transmembrane pressure drop along the length of the module. Now, you will be having, so what is this? If j is constant, for this particular case we are considering j is constant. So, mu is a property which is assumed to be constant, h is the dimension. So, we assume, so the right, according to our assumption, the right hand side becomes a constant. Okay. So, therefore, this equation has to be solved, and it is very easy to solve this equation, and one can have so you require two boundary conditions to solve this equation. The first boundary condition will be at x is equal to 0, your delta p will be nothing but delta p in. Okay. And what will be the other boundary condition? The other boundary condition will be obtained from the definition of q. How is that? If you rearrange this equation, this becomes actually you do not know what is the value of delta p and x is equal to L, because basically that is the objective of this exercise. What is the delta p at the x of the L? That means at the end of the module, so that you can estimate what is the total pressure drop over the full length. So that accordingly you can design a pump so that the flow rate will be maintained or the pressure will be maintained inside the thing. But you require to have one more boundary condition. So, one more boundary condition must be coming from x is equal to 0. So, what is that boundary condition? That will be obtained from this definition. If you rearrange this equation, that you will be getting d delta p dx will be nothing but minus 3 mu divided by 2 h cube w times q. Okay. And at x is equal to 0, the right hand side, in this case the Q will be nothing but Q in. Okay. So, again this is an example, the second boundary condition is an example of a physical boundary condition. Okay. So, since the initial conditions, the flow rate is known to you at the inlet of the module, one can define the gradient of pressure at that particular point from the definition of this Q. Okay. So, using these two boundary conditions, one can solve this equation and get the relevant expression of the pressure drop. As we have discussed earlier, since the right hand side is totally constant in this particular case, this becomes a the response or the pressure drop profile will be a linear one. Will be after one integration it becomes linear, and after second integration it becomes quadratic. So, finally, you will be getting a quadratic pressure drop expression. And if you really do that using the boundary conditions, if you really solve that, you will be getting delta P I minus delta P x at any x will be is equal to 3 by 2 by into mu h cube times w q I q in, that is x into 1 minus 2 j w x divided by 2 q I. Okay. So, this is the expression of the pressure drop. In fact, I have omitted couple of steps. Okay, the solution of that equation and evaluating the constant of integration by putting the values. So, you can really do that, and this becomes the final expression. So, this is the pressure drop at any x location. Similarly, you can find out the total pressure drop total over the module length L is nothing but delta P I minus delta P L, okay, is equal to 3 by 2 mu h cube by w q in times L 1 minus 2 j w L divided by 2 q I. J is meter cube per meter square second, W L becomes the total area, so it becomes meter cube. So, this gives an idea why it is multiplied by 2 on both sides, because twice JWL is the total amount of permeate that you are getting from, and what is the input? Input is QI. From QI meter cube per second, you are recovering 2 JWL meter cube of permeate. So, that gives some kind of definition of fractional permeate recovery. And delta Pi initial pressure minus, so delta Pi is nothing but Pi minus P atmosphere, and delta PL is nothing but P at L minus P atmosphere. So, P atmosphere will be cancelled out. So, this quantity really gives the pressure drop across the module. Okay. And if you remember, this whole thing becomes the delta P if you have J is equal to 0. Okay. So, that is the definition of Navier-Stokes equation, minus 1 minus F by 2. We call this factor as F, and what is F? F is nothing but fractional permeate recovery. This is very important. That means, if you are going to design a module, it is very important how much material you are feeding into the system. Suppose I am feeding into the system 100 meter cube per second in that rate, let us say, that is Q in. My aim should be what will be the maximum value of this F, okay, so that I can recover most of it, so that the system really becomes viable, economically viable. Okay, this F should be as high as possible. If H is as high as possible, then your delta P will be extremely large. By looking into the equation, you can see that the delta P becomes extremely large. Okay. Now, we will go to a tubular module and see how the system can be modified. In case of tubular model, we do the same type of analysis. Okay, from only case thing is we using, instead of rectangular coordinate, coordinate system, we go for the radial coordinate system. Okay, Navier-Stokes equation or equation of motion for this geometry gives you q is equal to pi r to the power 4 divided by 8 mu minus dp dx. I think it's basically derived in any standard fluid mechanics book. Okay, so and here we will do the assumption that actually again I will emphasize that you should know the limitation of this equation. This equation is derived for the impermeable wall, but in our case the wall is really permeable, but it doesn't matter because q will be the velocity in the axial direction will be in the order of meter per second, and the velocity in the normal or permeable direction will be in the order of 10 to the minus 5 or 10 to the minus 6 meter per second. So that really doesn't affect much. Again you do an overall material balance. So this gives a relationship between q and dp dx, and we have already seen that dp dx is nothing but d delta p dx, that is the transmembrane pressure drop. Now overall material balance over a differential element, again we will do over a differential element. This is location the located at x and x plus delta x. Okay, and it is coming out, and the total area where the permeate will be coming out is nothing but 2 pi r delta x, right, 2 pi r l. So 2 pi r delta x, L is nothing but delta x in this particular case. So if you write that down, what you will be getting is rho q at x minus q at x plus delta x is nothing but minus rho permeate, is rho permeate times j times 2 pi r delta x is equal to 0. Okay, this equation can be simplified to give you dq dx is equal to 2 pi r times j. Okay. Now you have the other equation. So this is the governing equation of flow rate. So you will be having, if the flow rate is decreasing because there are suction on the wall. Okay, physically it signifies that. Now this can be connected. So so if you look into the expression of q, pi r to the power 4 divided by 8 mu minus d delta p dx. I am just expressing dp dx by d delta p dx because they are identical. Okay. Now these two can be connected. How these two will be connected? You just take the differentiation, make the differentiation of this equation both sides with respect to x. Okay, and the left hand side dq dx, just substitute the value of 2 pi rj there. So that way you will be getting the governing equation of delta p, right. So you differentiate this equation with respect to x, dq dx is nothing but pi r to the power 4 8 mu minus d square delta p dx square, then equate these two. If you do that, what you will be getting is that d square delta p dx square is nothing but 16 mu over r cube times j. So this is the governing equation of transmembrane pressure drop, how that is varying as a function of x. Okay. Again, you will be having the two boundary conditions. You require two boundary conditions on delta p to solve this equation. They will be identical, but at x is equal to 0, you had at x is equal to 0, you have delta p is equal to delta p in, and at x is equal to 0, at the same boundary, you will be having just evaluate this equation at x is equal to 0, then q will be replaced by q in, and you will be getting a condition on d delta p dx. Using these two boundary conditions, you can solve this equation, but in this particular case, since j is constant, again the right hand side will be constant, and you will be landing up with a quadratic equation, quadratic in x. So the final form of solution pressure drop becomes delta p I minus delta p at the location x is nothing but 8 over pi mu r to the power 4 qi x 1 minus j r x over qy. Okay, and for the total pressure drop, total axial pressure drop across the module becomes delta p I minus delta p L is equal to 8 over pi mu by r to the power 4 qi times L 1 minus f over 2 pi. Okay, I will define that. So what is f? F is nothing but fractional recovery of the feed. Two pi is multiplied for both the sides, that will give you a 2 pi RL. 2 pi RL is the total surface area. So it gives the f really gives you the fractional recovery of the feed. That is very important. How much how much of the feed can be recovered in the permeate so that the system becomes feasible. Okay, so this is nothing but 2 pi RL times J divided by Qy. So this is the total flow rate that you are going to get from the permeate side in terms of, let us say, meter cube per second or meter cube per hour or liter per hour, and this will be the total feed permeate flow rate, right, and this becomes the feed flow rate. So basically, in an actual module or in an actual system, this will be specified to you that you would like to set up a plant of, let us say, 90 liters 100 liter per hour or something like that. So you must be having this fractional recovery will be more or less specified. In order to achieve that fractional recovery, what will be a pressure drop that you can calculate, right? If you can calculate that, then you can design a pump to run the system. Okay, that is the idea. So we stop here. In the next class, what we are going to do, we are going to move from a more realistic situation where compared to this assumption, the major assumption that is involved in this particular case, that the permeate flux is constant. Okay? Thank you.